Good morning, ladies and gentlemen. I'm Hein Wessels, and this is my colleague Jürgen Lüdemann. We are representing the Electronic Systems Laboratory of Stellenbosch, South Africa. We have more co-authors. One of them is sitting at the back there, and the other is still at home. We are here today to present to you our entry to the Deorbit device competition, which we came up with this year. Now, a little bit about Stellenbosch. We are mostly known for our amazing vineyards and luxurious wines, but when we put our heads together, we can make some amazing satellite products as well. During the course of this presentation, we're going to look at why we chose graphene foam as our material, how we can create a sail from this foam. Then we're going to look at how to put this foam sail inside the small space available in the CubeSat, and then some risks involved and some system designs. Now, as you all know, the Deorbit device or the space debris has become a big problem in the modern age and needs to be mitigated. And there's two main solutions to this problem, which is active debris removal and adding a Deorbit device to all future satellites. So we decided to focus specifically on CubeSats as set by the mission requirements, and to avoid the use of complex propulsion systems, as they are not yet really feasible for small CubeSats. Now, to avoid the use of propellants, we needed to make use of some external force available in space. And there's three main external forces available. Solar radiation and electromagnetic forces are very dependent on the satellite's orbit, especially the orbit inclination, which makes this mission-specific design very hard to design for, or general case design hard to design for. These forces are also very directional, for example in direction to the sun vector or the Earth's magnetic field, which means that you would need active orbit or active attitude stabilization, which makes the system more complex. Therefore, we decided to make use of the aerodynamic forces available in space. These are only mainly dependent on the orbit's altitude, which makes a more general case to design for. But more importantly, passive attitude stabilization is possible. Now, to utilize this force, we decided to create a sail. And there has been a few sails designed and deployed, a few of them in space. But the big problem with these sails is the release mechanisms. They consist of complex mechanisms and actuated booms, which has a very high risk of failure. Therefore, we decided to design around this thing. With the design objective of significantly reducing the orbit lifetime with a reliable self-deploying sail, we came up with a graphene foam deorbit sail with a Failsafe release mechanism. This sail will be able to passively deploy without any moving parts. The drag sail, and this is because the sail will consist entirely of graphene foam. The device will also come equipped with two independent and separate release mechanisms to ensure that this device deploys. Now, why did we choose graphene foam? We were looking for material that is very lightweight, as well as being very elastic, such as a sponge. This is so that we can fit the sail inside the CubeSat, in the small space available in the CubeSat, while still, when deployed, has a large surface area. And then we found this material called graphene foam. Graphene foam doesn't only excel in these requirements, it has a lot of other favorable properties as well. It's thermally stable over a very large temperature range. It's fairly strong and fairly flexible. Since it's quite a new product still, it's still quite expensive, but it's still affordable for some decent research and development. But we expect the price to drop, as seen in similar trends with chemical vapor deposition that is used to create silicon wafers. Graphene foam is a conductor. Now, conventional sails use mylar. Mylar isn't conductive, which makes grounding of the sail fairly hard. Then, during storage, the static charge builds up on the sail, which can cause problems with deployment. Therefore, since graphene foam is a conductor, grounding won't be an issue. We also don't expect graphene foam to have problems with outgassing, although the outgassing effects of graphene foam has not been tested specifically. However, a very similar material called hexagonal boron nitride is outgassing safe, and we expect the same results. Now that we know how and what material to choose to use, we needed to determine how this material will behave in space to design our sail. And the two main constraints in designing the sail is the surface area and the drag coefficient. And the drag coefficient of graphene foam has not been determined yet, so we needed to estimate this value. To do this, we assumed free molecular flow, since the device would be mainly in operation above 200 kilometers. And then to model the collisions between the air particles and the sail, we used the industry standard Sentman model, which models the collisions as the air particles being absorbed by the sail surface and then being diffusely reflected or re-emitted. Next, we needed the accommodation coefficient. Oh, and this is shown on the right hand there. Next, we needed the accommodation coefficient. Now, the accommodation coefficient describes how well the air particles and the surface of the sail reach thermal equilibrium, which affects the momentum efficiency, or the efficiency of the momentum exchange between the air particles and the surface. And this, which means in turn that it describes directly how effective the sail will be. Now, the accommodation coefficient of a material can only be determined experimentally and has not been determined for graphene foam. But it has been determined for graphite, which is very similar to graphene foam. Now, when you look at the collisions between nitrogen and graphite in space, it results in an accommodation coefficient of 0.4, which results in a drag coefficient of 3. Now, this coincides with commonly used value for a flat plate in space, such as seen in books like SMAD, and is also the nice conservative value that we decided to use in our simulations. But this is not the best value that we expect. When you look at the accommodation coefficient with collisions to oxygen particles in space, this value increases, the accommodation coefficient increases to 0.9, which results in a drag coefficient of 3.8, which is much better, much better. We could also prove that the sail would be passively stable, since we are planning to, since we put the center of pressure behind the center of mass. This means that we won't need any active attitude control during deorbit time. Now that we know what the drag coefficient of the sail, we needed to decide how big we want to make the sail. Therefore, we ran some simulations. Now, we looked at took the solar cycle into account and looked at two main scenarios. The first scenario is the expected case. This is where the device is deployed on the date as set by the mission requirements. The second scenario, represented by the dotted lines, is the approximate worst case, and this is where we deploy the device in the start of the solar minimum. All these simulations also run from a starting altitude as stated by the mission requirements. Then, to decide on the sail, we looked at how long these CubeSats would take to deorbit without any deorbit device, and decreased that time by 75%. The results is shown in the table below. And for example, the 3U would then need a 0.12 square meter sail, which means that for the mission, we expect a deorbit time of just over 2 years, or about 2 years, and a deorbit time decrease of almost 90%.
So to passively deorbit this, to passively deploy the sail, we make use of a totally graphene foam structure. This consists of a square sail base supported by the cross booms and attached to the satellite via the tether. So we designed for 300 kilometers altitude. Anything lower than this, and we don't mind if the sail actually breaks, because the satellite will naturally deorbit rapidly. So for the tether, we size it using ultimate tensile strength, and we came up with the following dimensions for the 1U and for the 3U. The length, however, is dependent on the sail base. So we make sure that the tether is long enough such that the sail base doesn't snag on the spring-loaded doors when deploying. When we consider the boom, we model it as a cantilever beam. This beam, or the boom, has to support the square sail base when undergoing deflection from the aerodynamic drag. So we came up with the following dimensions for the 1U and the 3U. And we said we want a maximum deflection of 5 degrees so that we can assume that the surface area is practically 100% efficient. Okay, now that we have a nice simple sail structure, somehow we need to fold this. But when we fold it, we need to consider a few things. We may not roll up the sail with a tighter radius than 0.8 millimeters. We may not compress in any direction more than 98%. We need to have space for the electronics to actually actuate the burn wires. And the volume of the payload has to be reasonable for a CubeSat. So over here we have an overview of our proposed folding method. This is the top view and the side view of the sail. So this is before it's folded. So the first thing we do is we compress the tether along the x-axis and we roll up the sail base along the y-axis as seen in B. Then lastly we compress along the z-axis the rolled up sail base. Please note, to avoid confusion, this is just an overview where the only thing which changes between our two folding methods is the rolling up of the sail base. Everything else stays the same. Okay, so this is our proposed design for the 1U. The way it is rolled up and folded actually aids passive deployment. So the compressed tether over here, as well as the rolled up sail base, will push outwards once the spring-loaded doors are released. We also stay well within our structural limitations as given in the previous slide, as seen over here. Lastly, this gives us a total payload size of 38 millimeters. So this is our second proposed folding method for the 2U, the 3U, and larger sail requirements. It also aids passive deployment due to the way it's folded up, and it also uses the space more efficiently. Once again, we stay well within the constraints, the mechanical constraints given earlier. The total size of the payload in depth is 68 millimeters. And please note, the way we fold it is a lot more optimized compared to the previous folding method, which means we can scale it nicely to larger sail sizes. Now that we have the sail in the enclosure, we need to talk about the release mechanism. So we have a simple spring-loaded door, which is held shut by Vectran wire, which goes through two burn wire systems, and which isn't very novel at all. However, we add some nice degradable polymer over here. How that works is it's exposed to UV as well as atomic oxygen, and then slowly erodes over time. Now, the Missy Peace mission from NASA on ISS has done some research regarding this, and they claim they can get a 3% error margin when calculating the erosion rate. So we're quite excited to see how this will pan out. Over here we see the spring-loaded doors, and lastly a springboard. So the springboard is there just to give it that initial boost out of the box, where after the sail will naturally decompress to its original shape. Okay, now let's talk about the release circuitry. So there's two ways in which that Vectran wire can actually be burned through. Either the satellite bus will toggle the electronic circuitry to burn through the wire, or independent timer will actuate the burn. So here we see the independent circuitry, independent of the satellite bus. So here the satellite bus can directly deploy the sail. It can reset that timer. However, if we lose contact with the satellite bus, maybe if there's a power failure or the OBC fails, the internal timer the internal timer will count to a certain time, and eventually the battery it'll use its own battery to release the spring-loaded doors. Yes, and under normal operation, we charge with 20 milliwatts of power. Okay, so the biggest problems we have with sales in space is deployment thereof. We have greatly mitigated this through the use of a graphene foam cell, because this graphene foam cell passively deploys by just decompressing back to its original shape. We've also mitigated this problem by having a release system which is, well, we could nearly say triple redundant. That degradable polymer basically acts as a ticking time bomb, which, if all else fails, eventually it will release the doors and then deploy the cell. So the development strategy we propose for the cell is, after you have a prototype, first you'll have to do deployment testing just to see exactly how does the cell deploy when the spring-loaded doors are released. We'll obviously have to do environmental testing such as thermal vacuum and maybe radiation tests, and we can use Raman spectroscopy to actually verify these results, because it gives us a ratio of defects to undefected material. So we can do that before and after and see the increase in the change in the structural integrity of the cell. We will also have to determine the outgassing effects of the graphene foam, as well as determine the precise relationship between the thickness of the graphene foam as well as its minimal allowable bend radius. So in our folding methods, we maximize this bending radius so as not to go into a danger zone of maybe tearing the cell by bending it too tightly. So we can really optimize that, hopefully. Lastly, for the graphene foam, we'll have to determine the accommodation coefficient. Regarding that degradable polymer, we'll have to test for outgassing naturally and just verify its structural lifetime. So in conclusion, we are able to do this novel design due to graphene foam's very nice, convenient properties. We have shown a design which claims reliable deployment due to the independent electronic release system, as well as the self-deploying nature of the cell, and the failsafe release backup, which is the degradable polymer. We've also shown passive stabilization due to the center of pressure behind the center of mass, the reduction of the orbit time by at least 75%, and shown that it's scalable to larger than 3U cell requirements. So we've reached all the Deorbit device requirements. Yes, with all research done and optimization of production levels or methods of graphene foam, we're excited for future products such as these, and we are very excited for the future. So thank you for your time, and any questions?
Thank you for the presentation, and it's time for question. Okay.
So I don't remember the final numbers, but can you repeat the volume you take in the CubeSat?
Okay, so for the 1 unit was roughly 68 millimeters. 39 millimeters, and for the 3U was 68 millimeters.
Okay, sure, the numbers are fine. And the cost is from $40,000 to $70,000, something like this?
Yeah.
From your notes?
Yes, correct. So
yeah, the cost is still quite high, but as we said, we expect the prices to drop within the next few years.
Okay, thanks. Impact on the center of gravity, have you discussed that?
No, we didn't discuss that, but the object should be fairly light because it's a foam, and it's very symmetrical, so it's easy to model, and I don't think it will have that big of an impact on the satellite.
So I have a question about the graphene foam. I'm not sure about graphene foam, but it's something like a sponge, kitchen foam. So you can compress the graphene foam very large ratio. I see. And I have one more question about graphene form. Graphene form does not change its material properties during the storage in space. So you know the Deorbit device will be stored in space for several years, but during the period, the material is not changed.
Yes. Okay, so we are confident that it won't change in vacuum because it actually, in space, due to its very convenient temperature range which it can work under, but we are unsure exactly, especially when it is compressed, how it will be affected in vacuum. But we are confident that it will work favorably.
Can you show me the picture of the holdings method? Yes, this one. Yes. From B to C, you are compressing in X direction, right?
No, the Z.
From
B compressing, yeah. From B to C, compressing.
Z direction.
Yeah.
Well, in that case, already it is a rolled, right? And you are compressing some rolled seat to this direction. Can you do that? Is it the soft enough?
Yeah, so we'll have to design some special rig when we package this graphene foam cell. So, yeah, that will be a challenge for development. Yeah.
And so, did you estimate how much force you need to compress?
How much percentage compression?
Yeah, how much force?
Oh, yeah. It's quite small. It's very small. I don't have the numbers on me now.
And the structure can hold that?
Yeah, it should hold that.
Any other question?
Hi there. I just wanted clarification, is it a foam or is it a mesh? Because if it's a foam, then you're going to have air trapped in it. So I assume being graphene, it will hold itself together once it's deployed. But in the deployed state, the pressure build-up when it goes into vacuum may be enough to blow open your door. Whereas if it's a mesh, you can outgas. So I'm just wondering whether it is a graphene mesh or whether it's a foam. I think it's more of a foam, but during stowage, initially before launch, you can vacuum, roll up the sail in the vacuum chamber or something of the likes and make sure that there's no left air particles inside of the container to ensure that it won't blow open.
So, do we have any other question?
Thanks for the presentation. I think it's a very interesting approach. But I was wondering if, when you did the selection of the material, which other materials you assessed?
I'm sorry, can you repeat the question?
Which other materials you assessed at the beginning before you end up choosing this one, the graphene?
Yeah, one of them was silicon, some silicon foam which they use in airplanes due to its thermal properties. But all those other foams, we looked at quite a few, and one of these, they all fail either the thermal or compression or mass. So, because our restriction was 20 gram per centimeter cube. Or 0.2 grams per centimeter cube, which ours gets to 14 grams. Right? Let me just get the numbers correct. Okay, yeah, 0.014. So we wanted to do it initially with anything lower than 20 grams, or 0.02 gram per centimeter cube.
Great, thanks.
Nice presentation. My question is, what is the outgassing
performance of this material? Thank you.
Okay, so the precise outgassing of the graphene foam is unknown, but we did some research into similar materials such as hexagonal boronitrate, and they actually use that to cover other materials in vacuum to prohibit those materials from outgassing. So we're quite confident that the graphene foam will react similar to the hexagonal boronitrate. But yeah, we do not have a precise figure for that. Sorry, excuse me, again?
Boron nitride is not a good material for outgassing.
Well, they use it in the one study to actually cover the, I think it was some electrodes or such, to actually bring.
Boron nitride is not a good material for outgassing a lot. That's why they use this cover.
No, so the hexagonal boronitrate, they cover the, was some metallic rod which they had, and then they covered that metallic rod with the hexagonal boronitrate.
So I think we don't have time for more questions. So please, after the session, you can ask the speakers. So let's thank our speakers again.